In this lesson, we're going to talk about local or relative, and also absolute, maximum, and minimum values, and then finally critical numbers. For our first definition, it says let C be a number in the domain D of a function f. The function f has an absolute maximum at C if f of c is greater or equal to f of x for all x that are in the domain D, and the number f of c is called the absolute maximum value of f on D. The function f has an absolute minimum at c if f of c is less than or equal to f of x for all x in the domain D, and the number f of c is called the absolute minimum value of f on that domain D. We have a note here. It says an absolute maximum or minimum value is also called a global maximum or minimum value. The maximum and minimum values of f are also called extreme values of f. So here we have a graph of f, and I just want to point out a couple of things. This point right here is going to be our absolute maximum value. This is going to be a local minimum value. This is also going to be a local minimum value. And this is going to be the absolute minimum value. This endpoint is going to be neither, so it's important to understand that absolute min and max values, they can occur at endpoints. So that's why this value is the lowest value on the interval from A to E. So we call this the absolute minimum value. And then again, you can see that up here, this is the highest value, f of D. So we call this the absolute maximum value on the interval from A to E. This definition says the function f has a local, or it's also called a relative maximum at C, if there is an open interval I containing c such that f of c is greater or equal to f of x for all x in that interval I. That is, f of c is greater or equal to f of x when x is near c. The number f of c is called the local maximum value. The definition for local minimum is just the same, except it's f of c is less than or equal to f of x. And again, f of c is less than or equal to f of x when x is near c. And that number f of c is called a local minimum value. So here's a diagram that depicts that situation. You have your local minimum right here. So on this interval, you can see that this is the lowest point. Same thing here on this interval, this is the lowest point. So they're both local minimums. But this one is also an absolute minimum because it's the lowest point on the entire curve. Right here, this would be a local maximum because on this interval, it's the highest value. So it's a local maximum, or again, we call it a relative maximum. But it's not the highest point, that would be over here. So you can see, like right here, you can have a local and an absolute min be the same value. Or you could also have a local and absolute max be the same value. Or you can just have a local min and just have a local max. This example says consider the following functions. We have f of x equals cosine x. So I drew the graph of cosine from 0 to 2 pi, and you can see that at 0 and also at 2 pi, and then it will happen again at 4 pi, you have a local max, which is also an absolute max because the graph will never go higher than 1. And then also for cosine x, you'll have a local min, or also an absolute min, at pi, and then 3 pi, and so on. And again, for the same reason, this is a local min, so in this interval, it's the lowest value, and then also the graph never goes below -1, so it's also an absolute minimum, and it occurs infinitely on every odd pi. And then I wrote it out. Our minimum value is going to be -1, and that occurs at every odd pi. And then our maximum value is +1, and that occurs at every even pi. Here we have y equals x squared. So right here at x equals 0, the local and absolute minimum value is going to be a height of 0. And I wrote that out. F of 0, which equals a height of 0, is the absolute and local minimum value for f. And then as far as a maximum value, there's none because the graph just keeps going. For this graph, we have x cubed, and because the graph just keeps going up to infinity, there is no minimum value and there is also no maximum value. This example says the graph of f is shown below. Identify the following. So right here we have a local minimum because on this interval it's the lowest value. Right here we have a local maximum, same thing, on this interval it's the highest value. Right here we have a local minimum. And then if you look at the entire graph, it's also the lowest value for the whole entire graph from -1 to 4. So we would also call it an absolute minimum. This would be neither. It's not a local and it's not an absolute max because it's an endpoint, so it can't be local. And it's not the highest point on the curve. That occurs over here. So this is going to be the absolute max. And again, we don't call it a local because it's not on an interval, but it is the highest point for this curve, so we do call it the absolute max. And I wrote them out. F of 1 equals 5 is the local maximum right here. Local minimums are here, and I wrote that out as f of 0 equals 0, and also f of 3 equals negative 27. Our absolute maximum is f of negative 1 equals 37 right here, and our absolute minimum is f of 3 equals negative 27. And again, this point right here does not fall under any of the categories. The note right here says the above example suggests that some functions have extreme values and others do not. The extreme value theorem gives conditions under which a function is guaranteed to have extreme values. So here we have the extreme value theorem, or the EVT. If f is continuous on a closed interval from a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in that closed interval from a to b. So this right here is telling us that absolute maxes and mins can occur on endpoints, or they can also occur within the interval. So here's a diagram with 3 different graphs. Our first curve goes from a to b, and our absolute max occurs at c, and it's the y value f of c. Our absolute minimum occurs at d, and it's the y value f of d. Here we have the situation where our lowest value, our absolute minimum, occurs at the endpoint, and our highest value is occurring at c, so we have that same f of c height. And here we have two heights that are equal, and they are our absolute maximum value f of c, and then we have one lowest value f of d. This example says functions that do not possess extreme values, since the hypothesis of the extreme value theorem is not satisfied. Remember, for this theorem to work, if f is continuous on a closed interval, then it will attain an absolute max and an absolute min. So you can see that this graph is not continuous at 1, and because of that, it does have a minimum value, and that's going to be a height of 0. It occurs at 2. But this will not have a maximum value because there's a hole right here, and the graph does not attain that highest height. So because this graph is not continuous, the extreme value theorem hypothesis does not hold true, so therefore it does not attain both a max and a min value. So it has a min, but it does not have a max. Similarly, this graph is not continuous on a closed interval. Here we have an open dot, and over here we have a vertical asymptote. So this graph actually doesn't have a minimum value, and it also does not have a maximum value. Here we have for Mott's theorem, it says if f has a local maximum or minimum at c, and if f prime of c exists, then the conclusion of Fermat's theorem says f prime of c equals 0. For this first diagram, we have a local max at this first c value, we have a local min at this c value, and also both those c values, you have your slope is equal to 0. So Fermat's theorem holds true. For this diagram, we have a maximum value right here at c, but f prime of c doesn't exist. You can't take a derivative at a corner, so therefore we have f prime of c doesn't exist. And then we have a note here. It says the converse of Fermat's theorem doesn't work. So our example is x cubed. When you take the derivative of x cubed, you get 3x squared. And let's consider plugging in 0 for x. You end up getting 0. So the converse of Fermat's theorem says that if you take the derivative at some value and you get 0, then there should be either a max or a min there. But if you look at the graph of x cubed and you look at x equals 0, you can see that we don't have a max or a min. So again, the converse doesn't work. Our next definition says a critical number, or a critical point, or also it's called a critical value, of a function f is the number c in the domain of f such that f prime of c equals 0, or f prime of c does not exist. So again, if you have the situation where f prime of c equals 0 or f prime of c doesn't exist, then we call that value c a critical number for the function f. This example says find the critical numbers for the given function. So we're going to take the derivative, and then I'm going to drop down the 4 that was already there. Next, the derivative of x cubed is going to be 3x squared. And again, I just dropped down this 3. We'll simplify in just a second. The derivative of negative x squared is going to be negative 2x. And the derivative of 1 is 0. Okay, these 4's cancel, these 3's cancel. So we get x cubed minus x squared minus 2x. In order to find a critical number, we have two things we need to check. We need to check where the derivative equals 0 and also where the derivative does not exist. Well, this is a polynomial, so it's going to exist for all real numbers. So this part of the definition won't produce any critical numbers, but we can definitely set this equal to 0 and solve. When we set these all equal to 0, we get 0, positive 2, and negative 1. So these are going to be our critical numbers for the graph of f. For part b, we have f of x equals x to the 3/5 times the quantity 4 minus x. To take the derivative, we're going to use the product rule. So we get negative x to the 3/5 plus 3 times the quantity 4 minus x all over 5x to the 2/5. First, I want to check where this doesn't exist. This x has a root of 5, so we're good on a negative. That's not going to cause any problems. But right here we have x in the denominator, so we can't plug in 0. So our first critical number is going to be when x equals 0. Next, we're going to set this equal to 0 and solve. So what I want to do is make common denominators. We're going to multiply this by 5x to the 2/5 on top and bottom. When you multiply 5x to the 2/5 times negative x to the 3/5, we're going to add the exponents, so 2/5 plus 3/5 makes 5/5, or just x to the 1. So you get this fraction. Anytime you have one fraction equals a number, you can always put the number over 1. Now this is a proportion, so we can cross multiply to solve. Remember, when you cross multiply, you're going to multiply these, and you're going to set it equal to the product of these. So you get this linear equation, and then we'll go ahead and finish this. So our critical numbers are x equals 0 and 3/2. For this next example, we have f of x equals the absolute value of 3x minus 1. So this is an absolute value graph. If we set the inside equal to 0, that will tell us where the vertex lies. So when we set the inside equal to 0, we get 1/3, so the graph gets shifted to the right 1/3, and then I drew an absolute value graph that has a slope of 3. So if we think of the definition of a critical number, again, it's where the derivative does not exist, and also it's where the derivative equals 0. And if you look at this graph, the derivative doesn't exist right here at 1/3, so that's going to produce the only critical number for this problem. So our critical value for f is going to equal 1/3. This example says if f has a local maximum or minimum at c, then c is a critical number of f. Next, we're going to do the closed interval or table of values method. And what we're using this method for is to find absolute max and minimum values of a continuous function f on a closed interval from a to b. So we have our steps written out here. Step 1 says find the values of f at the critical numbers of f in that open interval from a to b. Then you're going to find the values of f at the endpoints of the interval. And the largest values from steps 1 and 2 is going to be the absolute maximum value, whereas the smallest number is going to be the absolute minimum value. This example says find the absolute maximum and absolute minimum values of f on the given interval. For part A, we have f of x equals x cubed minus 12x, and our interval is from -3 to 5. So first step, we need to find the critical values of f. So that means we're going to take the derivative of f. We get 3x squared minus 12. And first we check if there's any values where this does not exist, and there are none, so that doesn't produce any critical values. Then we set this equal to 0 and solve. So our critical numbers are plus or minus 2. Now we're going to set up our table of values. We're going to plug in our critical numbers, and we're going to plug in our endpoints into f. We're going to see which ones produce the largest and the smallest values, and that will be our absolute maximum and absolute minimum values. So I'm going to go in numeric order. We have -3, -2, then we have +2, and then finally +5. And we're plugging all of those into f to see which one produces the largest and the smallest value. So first we're starting with x equals -3. We're going to plug it into our function for x, and you get +9. Next we're going to plug in -2. When we plug in -2, we get 16. Next we're going to plug in 2, and we get -16. And finally we're going to plug in 5. So of these values, our largest value is 65. That's going to be our absolute max. And our smallest value is -16, so that's going to be our absolute minimum. So there's our final answers. For part B, we have f of x equals the square root of 9 minus x squared, and the interval is -1 to 3. So first we're going to start by taking the derivative. And to take the derivative, I want to think of this as quantity to the 1/2. So using the chain rule, here's our derivative. Next, this -2 and this +2 are going to reduce, and you end up getting -x over the square root of 9 minus x squared. So first thing I want to check for critical number is where this does not exist. If you plug in -3 and +3, you'll get 0 in the denominator, which is a problem. If you plug in bigger numbers than 3 or smaller numbers than -3, it'll also make a negative underneath the square root, also causing a problem. But again, look at our interval. Our interval only goes from -1 to 3, so we don't need to worry about plugging in -3 or -4, -5 in those values. We just need to worry about 3 and any number higher than that. But again, within this interval, the only number that overlaps would be the actual number 3. So regarding a critical number, where the derivative does not exist, the only one that's going to be in this interval is going to be +3. Next, we need to set the derivative equal to 0. And when we set this equal to 0, I can put this over 1, and then we can cross multiply because we have our proportion. And we get x equals 0, and that is in the interval, so that's our other critical number. So now that we have our critical numbers, we're going to plug them and the endpoints into our table of values to see which x value produces the largest y value and then which one produces the smallest y value. So we'll go in order, we'll go -1 first, then we'll plug in 0, and then this critical number is also this endpoint, and so last we'll plug in 3. So when we plug in -1, we get square root of 8. When we plug in 0, we get 3, and when we plugged in 3, we get 0. So we end up getting that our absolute maximum is going to be 3, it occurs when x is 0, and our absolute minimum value is going to be 0, and it occurs when x is 3. For part C, we have f of x equals x over x plus 1, our intervals from 1 to 2. So first step, we're going to take the derivative to find the critical values, and to do so, we're going to use the quotient rule. So we're going to go low, d high minus high, and then d low all over the low squared. So you end up getting 1 over the quantity x plus 1 squared. Our first critical value, we're going to look where this doesn't exist, and this function does not exist when x is -1. However, if you look at the interval is from 1 to 2, and -1 is not in the interval from 1 to 2, so that won't be a critical number for our problem. Next, we're going to take the derivative and we're going to set it equal to 0. We have a proportion to solve it. We're going to put this over 1 and then cross multiply. When you do so, you get 1 equals 0, and 1 doesn't equal 0, so that's a false statement. So this also doesn't produce any critical values. So that means when we set up our table of values, we're just going to plug in the endpoints. So we're going to plug in 1, and next we're going to plug in 2. So we end up getting 1/2 and 2/3. So our absolute maximum is going to be 2/3, and our absolute minimum is going to be 1/2. All right, guys, thanks for watching.